So we have a question here. Metal wire is used to connect the power supply to a lamp. The wire has a total resistance of 3.4 ohms and metal has a resistivity of 2.6 times 10 to the power minus 8 ohm meter. The total length of the wire is 59 meters. A. Show that the wire has a cross-sectional area of 4.5 times 10 raised to the power minus 7 meters squared. So solution, we can solve the first question here. So in this question, we know resistance, we know resistivity, we know length. So basically, we should relate resistivity to length and cross-sectional area, where resistivity is the constant. So resistance is equal to rho L over what? A. So that L becomes what? RA over what? Resistivity. So what is the resistance? 3.4. Sorry. We are supposed to make it the subject of formula. So A becomes what? Rho L over what? R. A is equal to what is rho? Rho is 2.6 times 10 to the power minus 8. Length is 59. Resistance is what? 3.4. Quickly, you bring out your calculator. So look at the part that has fraction, press the fraction, put all of this at the numerator. So you have 2.6 times 10 to the power minus 8 times 59. Then put this at the denominator, 3.4. And this will give you the cross-sectional area becomes what? 4.511 times 10 to the power minus 7 meters squared, which is approximately 4.5 times 10 to the power minus 7 meters squared, which is what you will actually show. So that becomes approximately the cross-sectional area now is 4.5 times 10 to the power minus 7 meters squared. That's that. B. The potential difference across the total length of the wire is 1.8 volts. Calculate the current in the wire. So we can easily use this using Ohm's law. V is equal to what? IR. What is V? 1.8. V is 1.8. Current you don't know. Resistance is what? 3.4. So I becomes what? 3.4 over what? 1.8. And that will give you 3.4 divided by 1.8. You press your calculator, that will give you 1.89 amperes. 1.89 amperes. Both of them are in standard units already. So, and the standard unit of current is amperes. So you have 1.89 amperes. We'll move quickly to the next question. Okay. Sorry. There's something there. Sorry for that. V is equal to IR. The potential difference is 1.8. Current is equal to current times 3.4. So that the current will be what? 1.8 over 3.4. Sorry about that. So you have 1.8 divided by 3.4. This will give you what? Is 0.53 amperes approximately. Is 0.53 amperes. Making I the subject of formula from here. That will be 1.8 over 3.4. Okay, so that is the current. Okay. Then we move quickly to the next question. The number density of free electrons in the wire is 6.1 times 10 to the power 28 per meter cube. calculate the average drift speed of free electrons in the wire. So I can clean this. If you need it, you can easily rewind. So if I clean this now, so the number density of free electron is given to be this. And remember, number density, how does current relate number density to drift speed? Current is equal to number density multiplied by elementary charge cross-sectional area multiplied by the drift speed. Is that okay? So the drift speed will be equal to current over NEA. So what is current there? 0.53. What is the number density of free electrons? 6.1 times 10 power 28. What is the elementary charge? 1.6 times 10 power minus 19. What is the cross-sectional area? That is the first thing you are asked to show, that the cross-sectional area is 4.5 times 10 power what? Minus 7. So the drift speed will just be, you put all of this in your calculator, you know what the current is, number density is given, elementary charge is a constant, and that is the cross-sectional area. You put it once again in your calculator, use the part of the calculator that has fraction. So you press the fraction, put this at the numerator, 0.53. You go to denominator, 6.1 times 10 power 28 times 1.6 times 10 power minus 19 times 4.5 times 10 power minus 7. You do that, your calculator will just give you the answer in no time. Your calculator will give you your answer in no time. Your calculator will give you your answer in no time. So the drift velocity there is 1.204 times 10 power minus 4 meters per second, standard unit. So you can round it up to two significant figure at the drift speed. You can round it up to two significant figure that the drift speed becomes what? 1.2 times 10 power minus 4 meters per second. Alright? So that is that. That is that. And you can always be tested as you are solving problem. You can be testing whether your calculation is correct. I know that 10 raised by minus 19 minus 7 will give you minus 26. So you have 28 times 10 raised by minus 26. That will be 10 raised by 2. By the time you take that across the cosine, so your answer should be having the raised to power 10 there should be raised to the power of a negative value. Okay? So the last one here, a different wire carries the current. The wire has a part that is thinner than the rest of the wire as shown below. State and explain qualitatively how the average drift speed in the thinner part compares to the rest of the wire. Remember that the average drift speed from here is given as current over what? NEA. So I can therefore say that here I'm looking at the variation between the drift speed and the cross-sectional area, because the current flowing through the thicker part of the wire will be the same as the current flowing through the thinner part of the wire. So the current is what? Constant. The current flowing through the thicker part of the wire is the same as the current flowing through the thinner part of the what? Of the wire. So the current is what? Is constant. The number density of charge is a material constant. Is the same. Elementary charge is a constant. Therefore, the drift speed is inversely proportional to the cross-sectional area. Okay? Therefore, the thinner part of the wire is having a smaller cross-sectional area compared to the thicker part of the wire. Therefore, the average drift speed in the thinner part of the wire will be more than the other parts of the wire. So how do we answer that one without wasting time? We can easily say, let me just try to make it small thing. Average drift speed is inversely proportional to cross-sectional area. For constant current. Therefore, average drift speed will be greater at thinner end of the wire. Is that okay? So average drift speed will be greater at the thinner parts of the wire, which you can easily see here. Current is constant, number density at the elementary charge is constant, average drift speed is inversely proportional to the cross-sectional area. Therefore, the average drift speed will be higher at the thinner part of the wire.